Right.
Okay.
Welcome everyone to the HDR-Nets workshop. Now it's a time for our second keynote talk. Our keynote speaker is Professor Ahmed Helmy, and the keynote title is Data-Driven Modeling and Design of Network Mobile Services, playing with matches, flutes, and cellos. Professor Ahmed is also the graduate director and the steering committee chair and founding director of the Mobile Networking Lab at the Department of Computer and Information Science and Engineering at University of Florida. He received his PhD in computer science and the master degree in electrical engineering from the University of Southern California. And a bachelor's degree in electronics and communication from Cairo University. Before joining the University of Florida, he was on the faculty at the University of Southern California. He was a key researcher and main contributor to the protocol independent multicast, PIM-SM, also the Narrow Simulator NS2, the Stress project, the Important Mobility tool, and the MobiLab Trace library. He received the National Science Foundation NSF Career Award and has led, or is continuing to lead, numerous projects funded by NSF, NASA, DARPA, Intel, Cisco, NVIDIA, Nortel, HP, Pratt & Whitney, Siemens, and others. His research work and papers won over 10 awards, best papers, best posters, demos, mobile application from the top IEEE and ACM conferences, including ACM Mobicom, IEEE Infocom, and ACM SIG Spectral. He was an honorary fellow at the Tech University Munich and term professor at University of UF. His work has more than 16,000 citations, and his H-index is 55, and he's a IEEE fellow and ACM distinguished scientist. So without further ado, I welcome Professor Ahmed Helmy, and I leave the floor for him.
Thank you, Tamer. This is a great pleasure to be here. And let me just share my slides. Okay, let me know if you have any problem seeing this.
We see it there perfectly.
Okay, great. Okay, so my name is Ahmed Helmy. I'm a professor and the graduate director at the Computer Information Science and Engineering, or SICE department at the University of Florida. And in this talk, I'd like to take you.
If I can interrupt, if you can turn on the camera, if it's available, that would be really great for the interaction, just for the
okay,
audience.
let me stop the sharing. I'm not sure. Okay, so let me get back to this. Sorry about that. Yeah, the lighting may not be perfect. So let me see.
We see you perfectly.
Okay. See here. All right, so let me share the slides again. I'm clicking share, but it's okay. It's taking its time. I don't know. Something is happening. Can you still hear me?
Yes.
Yeah, I think the camera did something. Yeah, it's stalling. It is stalling. Yeah, I got this wait symbol, unfortunately.
Okay, too much. That's okay if you can turn it off.
Yeah, if I can get to it, if I can just get to it, that'd be great. But I cannot at this point. I may have to leave and join again.
Okay.
Chrome is not responding. Yes. Okay. Yeah. All right. Wait to respond, close the program. Okay, may have to join back again. May
Sure.
have to close this and go back again. During these COVID times, I hope you all are safe, you and your families. In this talk, I wanted to share over 15 years of experience and journey with my group and work on the data-driven modeling and design of networked mobile services with case studies on playing with matches, flutes, and cellos. So here's a quick outline of the talk. I'll start with an overview of the TRACE framework and give a motivation of why we need data-driven modeling and design for protocols. And then we're going to start the bigger picture framework and then use that framework concretely in two categories of case studies. The first one is going to be on pedestrian modeling and similarity, where we're going to talk about mobility traffic integrated models, and we're going to analyze flutes and cellos. Okay. And the second category of application is going to be on vehicular mobility and similarity using imagery data and playing with matches for shared transportation. And given the time, we may be able to go into some futuristic applications, particularly on mobile health. So let's get started with the first component of the data-driven modeling and design. And let me just give you an initial history and background for this. So I was lucky in the mid-90s to work on the internet standard for IP multicast for PIM sparse mode. And I worked all the way from the design to the testing phases on it. And along with the PIM team, we realized that we lacked a lot of tools for evaluation of protocols. So we designed and developed Network Simulator NS2. Some of you may have used it. During the process of protocol evaluation, we realized two different things. The first is that we need a more robust test generation process where our test suites need to exercise worst case scenarios and robustness of the protocol. And that motivated also the mobility aspect where mobility stresses protocols. The other realization for the team is that we needed representative scenarios that are grounded in reality and have realism to them. So these two components, robustness and realism, led to the birth of the data-driven mobility modeling in my group, where we had several case studies on the important framework and trace-based models like TVC and Cobra community models, and large-scale simulations of vehicles using en route. Utilizing the insights that we gained from the analysis, we were able to also design several protocols and models like profile casts and the flutes and cellos study and the playing with matches for shared transportation. We also worked on location-based services and other wireless mobile networks, and I'll try to touch upon the Intelligent Hospital project that went on for about 7 years on contact tracing well before COVID-19 hit. And if there's time, we'll talk about mobile health potential applications. So why do we need the data-driven protocol design paradigm? Let me first start with the old paradigm that I, my group, and many others have used for the design of internet protocols in ad hoc networking. We generally start with a general purpose protocol, and we evaluate it using generic models like random mobility, exponential traffic distributions, uniform session distributions, or Poisson distribution of node placements. The hope is that by the time we reach the deployment phase, is that we can modify and improve the performance of the protocol in order to be successful in the real world. The main problem with this paradigm, however, is that the use of these unrealistic models of random mobility and exponential traffic result in suboptimal performance and, in many cases, write-out failures due to the lack of the context in the design phase. Okay, so the proposed new paradigm here is to turn this upside down, and instead of starting at the protocols and ending in the context, we actually start from the context. We trace it, analyze it, and understand it, and then use that understanding to drive the design of classes of applications using parameterized protocols, and then harness all that data power to fine-tune the protocols and its parameters. And because we started from the context, we have a much higher chance of succeeding in the real world. So in order to realize our vision of the data-driven protocol modeling and design, my group actually, over the past 15 years or so, have developed and refined and implemented the TRACE framework. And the framework is very simple. It has several components as seen in this block diagram. And it starts with developing the library of traces. And we started collecting the data in 2004, and we built literally dozens of billions of records in the trace, collected from wireless LANs on different campuses and webcams all around the world, in addition to other contexts as well. So we have right now over 40 terabytes of data and still growing. Depending on the problem that we're trying to solve, we find a suitable representation for the data, like vectors, matrices, or graphs and networks. And then after that, the statistical analysis can take place to understand the first trends in the data using curve fitting and time series analysis like self-similarity or long-range dependence. Then more sophisticated data mining, machine learning, and AI techniques like clustering and classification and so on can take place to better understand many features of the data. And eventually, we'll take all that insight in the employment phase and develop more realistic models and more efficient designs for mobile applications and services. So I'm going to use this framework throughout the talk, and we're going to go through it step by step in the different case studies. But let me start by talking about the first component, which is the trace itself. So there was a vision to have this community-wide mobility library, and the library would house many measurements from campuses, from streets, from municipalities, and so on. But not only that, the vision was to establish a library of realistic models for mobility, for behavior, for traffic, trust, privacy, and so on, in addition to benchmarks and test suites and network analytics tools. So I had this vision in 2003. In 2004, we started collecting data from USC, Southern California, where I was at that time. And then we continued collecting from University of Florida, and we collected from many different places in the world using webcams in many different cities. We'll talk about those specific data sets later on. And we built the MobileLib website. So MobileLib is housed right now at the University of Florida. Internally, we have over 40 terabytes. We can't share that because it's just too big. So you'll find many samples, not only of the data, but also we have the code and the algorithms shared, so you can reproduce things. We also are working on a one-click reproducibility where you have a Docker image of all the packages needed. So you can just one-click and you can generate the exact same or very similar graphs and figures to the ones that we have in the published papers recently. right? So right at the same time where we started this, there was another parallel effort. You probably heard about Crawdad in Dartmouth, and Dave Coates was the lead for that. So he and I, talked a lot, and then we went around knocking on everybody's doors, and we went to people from, MIT, Georgia Tech, USC, and many other places, San Diego, and so on. And we said, if you have any data, give it to us. Please give it to us, and so on. And we kept knocking on the door until they said, okay, here's the data. Go away. We don't want to see you again. All right. So we ended up actually with dozens and dozens of these data sets that are now available, particularly through Crawdad. We also contributed to Crawdad ourselves. So Crawdad is supposed to be a repository. Mobileye is supposed to be more of a links kind of thing with our own internal thing, but also linking to other resources somewhere else. And as we will see, there are many different types of traces. Some were called wireless LAN traces. Some are collected at conferences, and some are encounter traces. Municipalities also have a lot of wireless data these days, taxi cabs. And lastly, we have vehicular imagery data that we used very effectively over the past decade or so. So that's the first component. And then we're going to take these data sets and do a lot of case studies with them. So let's go into the first category of case studies. The first one is for pedestrian mobility modeling and similarity. And we're going to talk about mobility modeling and the integration of traffic and mobility together in one model, and also the flutes and the cellos. Okay, I haven't given out what flutes and cellos mean yet, so there's some suspense here. Especially if you're a musician, I think you will like this. All right, so let's look at a multidimensional space here, and there are many different multidimensional spaces we'll talk about. What this one basically talks about, are we going to talk about individual patterns or collective and group patterns or pairwise patterns as in encounters and contacts? So we'll start with the individual patterns first, and let's see the case study that we started with there was actually trying to identify parameters and features and the traces that were not captured by the models back then. So we looked at location preference and periodic reappearance basically as the two main features. We looked at other things, but I'm going to just only features these two for now. And we used 5 different traces from wireless LANs and DHCP traces from different campuses around the US. And this was a month-long trace. And here are some of the entries where you can get the MAC address for the associated device, the access point name, and luckily this has location information in many cases, including the building, the floor, and the room, so we can associate the activity with the location. And then you have the timing information as well. Of course, this is anonymized, so we can't link it back to users. We're very careful with the privacy issues. But as you can see here, we analyzed the features in the trace, and you can see very clearly that the models, the random direction model, the community model here on the left, are flat when it comes to the location preference, whereas the other traces, the real-world traces, show heavy skewed distribution with respect to the location. It turns out that on average, a user would spend 95% of their online time associated with the top 5 most visited access points. Okay, that's nowhere to be seen in the existing models. Similarly, the repeated appearance at the same location, again, if you look at the community model and the random direction model, have to be flat. They cannot capture these features, whereas we can clearly see daily and weekly patterns and other patterns in which there is repetitive appearance at those locations. Okay, so we took that insight, and what we did was we proposed a new model called the time variant community model, or TVC model. And this attempts to incorporate 2 different elements. One is a spatial element where you add the concept of community or locations where users have higher chance of associating more than other places. And the other one is a temporal element where that community can vary with time. So in the morning, it can be going to classes. At noon, it could be going to the food court, and the afternoon could be going to the library or so. So this attempts to capture both the temporal and the spatial aspects. And we implemented that. We derived the parameters from the traces, and then we validated that with many different traces. Just as an example here, we can get a very nice match on both the location visiting preferences and the periodic reappearance between the model and the real data. So that shows that we can very effectively use, at least at the individual level, the data to develop more realistic models. Okay, so that was one of the first dimensions to cover, right? So the individual patterns. Next, we took a look at collective patterns or groups. Okay, so we're going to look at that dimension right now, where we try to identify groups of users that have similar behavior or interests. Okay, and you know, we have to define what behavior is, and it can be defined in so many different ways. But just as a very simple example, we look at the user association. Okay, so if a user goes to the office, the class, and the lab, and spends 20%, 40%, and 40% of their time there, then you get what we call an association vector for that day of 0.2, 0.4, 0.4. Okay, the devices can locally, in a privacy-preserving manner, keep track of that association vector day in and day out, and you end up with what we call the association matrix. Okay, so the rows are the days, the columns are the locations, and the entry is the percentage of time spent at that location on that day. Again, a very simple representation, yet it can be very powerful. So what we effectively can do, again, in a privacy-preserving manner, if you have these two nodes in this multi-dimensional behavioral space defined by the association matrix, you can actually talk about their similarity or differences. And without going into a lot of the math, we can use the eigenbehaviors of these matrices and talk about their differences. Okay, so once you have this metric and similarity, you can talk about clustering users into groups. So where a user would fit in a group of other users that go to the same places and spend roughly the same amount of time there. Okay, so that's the main idea, and you can see that this can be very powerful. So we applied this technique to many different traces for different campuses. As you can see here, also the result shows very clear clustering and the existence of these clear groups of users of similar behavior. Of course, the actual graph will depend on the structure of the campus and the data itself. So this was actually eye-opening for us. This was the first that anyone had talked about this and done quantitatively in a mathematical way, in a very concrete way. So by knowing this insight, we were actually inspired to talk about a new communication paradigm that harnesses this idea of similarity groups. So we proposed something called profile cast. And profile cast, instead of targeting the message to a machine address, like an IP address or a MAC address, what we do is we target it to an interest profile. So if I have a talk about music, of someone using computers to visualize music or something, I want to send this message to people who are interested in music and technology or computer science. The nice thing about this is that we developed a protocol that was implemented and demoed at ICNP before, using delay-tolerant networks, where the device actually just sends a message. It doesn't know where it's going, but it embeds the eigenbehavior of this matrix for the target profile that you want to target. And locally, again, in a privacy-preserving manner, you can try to match this with the other profiles for the other users and deliver it where it reaches a specific similarity score. What's even nicer, you can use what we call the gradient ascent approach, where you have these similarities spread around the community just naturally. And you have this gradient built in naturally without any overhead from the protocol side in the community, where you can hop from one node that is not similar to another node that is more similar and more similar and more similar until you actually hit the group that you want to target. So this has been proven to be very, very efficient. It cuts about 94% of the overhead from flooding, and it can achieve very high delivery ratio. One downside is that it's delay tolerant, so you have to incur some delay. However, at the same time, the delays that you incur actually can be sidelined or circumvented by using some kind of a centralized approach, but then you may lose some of the privacy preserving aspects that you have. All right, for the sake of time, I'm going to skip the group mobility. Okay, so, okay, sorry, let me go back. So here, so far for profile cast, we used this location visitation profile as the indication of interest. And as you can potentially imagine, that there are many other features that can capture this interest, whether it's load or device types or encounters, friendship, and so on. So there's so many different dimensions that we have not captured in this study. So in order to capture all these other dimensions, we introduced this multi-dimensional space. And there's been a lot of work on mobility, including from my group and many other groups. There's been a lot of work on traffic by itself, but nothing that combines both. The TVC and the Cobra model, Cobra, by the way, is something like TVC, but it harnesses the group similarity that we just talked about. And I skipped that just for the sake of time because we encountered some technical problems. So in those studies, we tried not only to capture mobility, but also try to capture some social context in it. In addition to that, we've had some studies to talk about the device types, how to classify devices in the trace into laptops and smartphones. We'll talk about that a bit later. And we've also talked about some predictability in other groups have. But there was no other study that tried to capture all of these different dimensions together. So the study that I'm going to present now is called the Flutes and the Cellos, and it's attempting to capture many of these features all together. In order to capture all these different dimensions, we developed the Flames framework. And this is a multi-tiered framework that starts from the data at the top. And then you have the sanitation process, parsing the data, developing the different features and so on, and even inferring some things like device types, which are not explicitly in the trace. And then once we establish that, then you can do the analysis of the different relationships for this, what we call the data cube, between traffic and mobility on the one hand, temporal dimension and spatial dimension, and then through the laptops and the smartphones. So you can see so many different dimensions there. And in the end, we try to apply this using many machine learning and AI techniques, deep learning techniques, and so on to quantify the value of this integrated model and see if we can solve a lot of pressing problems using this multidimensional approach. All right, so here's the flutes and the cellos part. And first I have to give credit to Professor Mustafa Ammar from Georgia Tech for suggesting the name cello mobility and permitting us to use it in this talk and in this paper. Basically, if you're a musician, you would know that playing a cello, you would have to sit down. Okay, so this is a funny thing. I can't play the video now, but you can probably find on YouTube. It's from Woody Allen's Take the Money and Run movie, where he plays the cello, but he insists on joining a marching band. All right, so he takes a chair, he sits down, starts playing, and sure enough, the marching band moves on, and he's left playing by himself in the street. So lesson number one, if you play the cello, don't join a marching band, right? Lesson number two, the way that we use our laptops is exactly similar to this cello, where you have to sit down to use it. And once you stand up, you usually turn it off and move. Okay, that's lesson number two. Lesson number three is that many of the traces, actually most of the studies out there, use traces from 2008 and before, where we did not have smartphones, where we only had laptops. So you can imagine that the devices that we have today are used in a very different way. than the cellos. And they're used more like flutes, where you can use it on the go. Okay, so that's the flutes and cellos for you. All right, so basically the first step to understand the difference between flutes and cellos in this multidimensional space is to look at the data. So let's look at the first few data sets. And this is one of the biggest data sets we've had so far. It was collected in 2011, 2012. And one type of trace is called a wireless LAN trace. And this is basically the usage trace that, when a device with a specific MAC address associates with an access point, you can log that. And as we said, the access point has location information in it. So this trace has over 500 million records. It spans, approximately 480 days, and it encompasses 316,000 devices. Okay, and then it's 138 buildings at UF, which is about 2,000 acres. It's a huge campus. Okay, so this one talks about the usage of the devices on campus. But it doesn't talk about the traffic activity, which websites were accessed, how much traffic was injected, and so on. For that, we have another type of trace called the net flow trace. And the net flow trace is by far the largest trace we have. It's over 30 terabytes in size. It's about 2 to 3 orders of magnitude more than the wireless LAN traces, have 76 billion records in only 25 days. And it encompasses 80,000 devices, and the entries include the source and destination IP address and port number, and these can be resolved to websites and interests and so on. There's also the packet information and start and the end of the flow. We can also join this with the wireless LAN trace with the existence of DHCP records, which mapped IP back to the MAC address at that point in time, and so we can get the location information. All right, of course, there's auxiliary information and sources of data that need to be used, like schedules of classes and building lists and so on. We also do device type classification. That was a paper by itself, where we use reverse DNS to websites. And then there are specific websites that can only be accessed with smartphones. You can also use parts of the MAC address to have the manufacturer of the device, or at least the network interface card. We also did a lot of surveys to try out some sub-prefixes where some manufacturers like Apple have both smartphones and laptops, and using some kind of a algorithm to classify these, we were able to successfully, with high confidence, quantify or classify 97% of the devices as either flutes or smartphones or cellos or laptops. Okay, so that was the first step, sanitizing the data and inferring that information. The second step is to actually do this analysis and correlation. All right, so basically we have the traffic and mobility dimensions, we have the space and time dimensions, and we have the device types as well. Okay, and what we can get from this, and this is just a big picture, are these graphs that have the difference between laptops and smartphones. You can here see that there's a huge difference in the DHCP events, the number of active access points, the traffic volume that they inject, and so on. And this is over 25 days. So if you look at the x-axis here, you can very easily identify the weekly pattern, where there are 5 days of high activity and 2 days of low activity over the weekend, and that repeats over and over again. Okay, so we identified over 24 of these features, and we did some feature extraction and minimization techniques. And we looked at the difference of features between the flutes and the cellos, both the mobility features like the radius of gyration, the number of unique access points associated with, and so on. And also we had a dozen features, or more than a dozen features for traffic as well, for the number of bytes and packets and the total active time and so on and so forth. And what we're looking at here is the ratio of C over F, which is cellos over flutes. And as you can see here, we have some very big numbers and very low numbers here, which basically indicates that there are orders of magnitude, 2 orders of magnitude for traffic and 3 orders of magnitude for mobility features that are different between cellos and flutes. And as I mentioned before, most of the studies in the past had what we call pre-smartphone datasets, including our own. And this basically means that the characteristics in those papers only talk about the cellos, whereas the flutes can be very, very different. And there's definitely a very big motivation here to go back and revisit this area. I don't think we'll ever stop visiting this area again, because the devices change, behavior changes, as subsequently we have to update our mobility models. Another thing we looked at is the correlation between the traffic features and the mobility features. So you have the mobility features here on the y-axis, the traffic features on the x-axis. And this is done for weekends and weekdays and flutes and the cellos. And you can clearly see that there are some positive and negative correlations between these different models that no one has looked at or studied before, because there were no integrated traffic mobility models before. And this definitely is not captured at all if you develop the mobility models in isolation from the traffic models. And by the way, this is a 4-year-long study that was in collaboration with other universities around the world, like in Munich and Finland as well, particularly Jörg group. Okay, and after we've identified all the different features and so on, we can ask the question, so why bother? Why is this actually making any difference, or does it? So we took a couple of examples here and many, many others in our work to see if we can combine these features. Can we improve things? Okay, so one of the questions we asked is, can you use these features to classify devices? One would argue that we know that smartphones are much more mobile than laptops. So why don't we just use the mobility features to classify these devices? Okay, so and in turn, basically, if you use mobility features only, you get 65% success rate, which is pretty low. For the traffic, get 79 and so on. If you combine them, if you split them over weekday and weekend, you always improve. And basically, if you add some features like predictability features, you go up from 65% to 91%. So this was a classifier using support vector machine with 5-fold cross-validation. So it's a very simple classifier, yet by increasing the dimensionality and taking more features carefully into consideration, you can improve the classification dramatically. Okay. Again, this was not always the case. Sometimes you increase the dimensionality, you add to the noise, so it's not a clear cut here. But you can see the advantage of using this multidimensional feature space. Another area that we looked into, and I don't have time to get into that in detail now, is generative modeling. And basically, this can potentially be used to share the data in a privacy-preserving manner, so we can enhance the reproducibility of our results as a community. And basically, if we're using the traditional Gaussian mixture models, you can get about 84% accuracy with your regenerated models using these combined features. If you switch to something like a deep learning model, like a variational autoencoder or VAE, you get upwards of 92% accuracy. So that's, again, a dramatic improvement, and it can open the door for many more studies to come. Again, for the sake of time, I'm just going to skip over this part. Actually, let me just go over it very quickly. So we covered the individual and the group dimensions. This one is talking about the encounter dimension. And again, very quickly, an encounter happens or contact happens when two nodes are in proximity of each other, such that they can potentially communicate or transmit a disease or do some kind of social interaction. So here we define encounter as two nodes accessing the same access point at the same time. and we define different types of encounters. And then we ask the question, if two nodes have encountered each other, does that mean that they're going to be also similar in traffic? And it turns out that 93% of the time in all the buildings, the average similarity of encountered pairs is higher than those that have not encountered. The only exception to that are those encounters that are short-lived in places like bus stops or hubs and pass-by rates, people just passing by each other. So what does this mean actually to us? It means that we can potentially classify or predict, just by looking at the traffic patterns, whether two nodes have encountered each other, and even reason about the duration of that encounter. And this can be done very, very accurately with, again, deep networks using stack denoising autoencoder. Here, you can get over 92% or so of accuracy. And it's a question, can we use this information to improve contact tracing? Whereas right now, contact tracing depends on this physical contact, but it may not be possible always. So can we try to infer information from the traffic patterns and the activity of the users online to try to assume that or infer that or predict that they have encountered each other for a long time? And the answer could be yes. We've been able to do it very successfully, at least in this particular trace. All right, so the second set of applications that I want to get into, and again, I don't have a lot of time at this point, but I want to talk about vehicular mobility and similarity, which is a different set of data altogether. And unlike wireless LANs that we have on campus, we really don't have a lot of access to data sets for vehicular mobility. Not until recently, many of the Department of Transportations in different states are releasing different data sets and so on. We're looking at those as well. But they're much rarer to come by because of the restriction and the privacy for the transportation projects. So through some collaboration with the T-Labs research and TU Berlin, about 10 years ago, 2011 or so, my student Gautam Thakur and Ben Hui from TU Berlin, now he's at Helsinki, I think. We came up with an idea of tapping into webcams around the world and getting imagery data of cars on streets and highways. And sure enough, we were able to tap into, legally with permission, around 5,000 webcams from all around the world, all the way from India, Connecticut, Georgia, London, New York, Seattle. You can see many, many different cities here all around the world. And we collected about 140 million images, 7.5 terabytes. I think the number is much higher now, but this is only for that particular study. And these are images that are taken about every half a minute to 2 minutes. And they look something like this. And you actually have to process the images to get meaningful information. So one way we processed this information was to establish a time series for each camera by looking at the images and saying, how much occupied is this street? So this basically defines something called the traffic intensity, where this is, for example, is about 28% full, this is 55% full, and this is 93% full, which means that there's congestion. And there is a very efficient modified background subtraction algorithm. We had to modify to account for the perception of the camera. And then you can actually get very meaningful time series information. Okay, so here are some example of what we can do. So this is a camera over here with the blue colors mostly. This was a low traffic camera, maybe perhaps out in the suburbs in Australia somewhere. And this is over 42 days and from 7 a.m. to 7 p.m. Okay, and you can see also very high traffic here with the red one. I think this was downtown London or something. And you can also very easily see the weekends here in between the yellow in between the red. That's the weekends and irregular traffic This may have been somewhere maybe in Sydney or something. You can also see the rush hour in the morning from 7 to 9, and the rush hour in the afternoon from about 3 to 6 or so. Okay, so you can reason about the different traffic patterns all over the city. All right, so one of the questions we asked ourselves, now that we have these time series and processes, can we capture them with certain distributions? And can we look at the self-similarity and long-range dependence for these traces? And again, the results are very interesting because unlike many of the models in the transportation literature that rely on what we call memoryless processes, like the Poisson process, the normal or exponential, and we all love to use these because they're very tractable mathematically. It turns out of the 700 plus locations we looked at, the better models that fit the data are heavy tail distributions like the Weibull, log logistic, and log gamma. And the traditional models have a much lower chance of success in capturing these stochastic processes. And in terms of self-similarity, definitely we found that this process for many of the locations, about 85% of the locations, had Hurst parameter of well over half, 0.5, which means that they are heavy tail and long range dependent. Okay, so that just tells you that these models, memoryless, simplistic models, do not capture much of the reality, and that was manifested in the data that we had. Okay, so that was based on individual cameras. What if we have multiple cameras? What you get is one time series per camera, and what you can do here is also do some spatiotemporal correlation. So instead of looking at one camera, you can look at multiple cameras and maybe try to do prediction. So using causality analysis, and now we're also using some deep networks and LSTMs and recurrent neural networks, you can actually predict where congestion is going to go in the city by knowing the data from the different cameras. Now, we could predict very accurately within less than 10% error, 30 minutes ahead of time in Sydney where congestion is going to go. So this can be very powerful in trying to ameliorate congestion and avoid delays and pollution and so on. Okay, so the last part I want to talk about here is playing with matches. And this is basically talking about trips and trying to match them for the purposes of shared transportation. Okay, so here's the heat map. I'm going to talk about the data in the next few slides, but this is a heat map of the trips. And basically, you can see this is the trip density in part of the city, and this is from 8 to 9 p.m. You can see very different density here and there. And definitely what you want to do is want to try to incorporate ride sharing, carpooling, car sharing, or many other transportation models to try to ameliorate, again, pollution, congestion, delays in the city. Okay, so the study of the trips and the similarity between these trips is essential in these services. We define a trip here by, 3 tuple, x, y, and t, where x, y are the location, t is the time. And one can just very simply look at the trips here, like, P1, P2, P3 are 3 trips. I would say, oh, P1 looks much similar to P2 and less similar to P3. But this is only looking at the space. What if they're not overlapping in time? Okay, how would you reason about the similarity then? So we have to have a combined spatiotemporal metric to capture this similarity. Okay, and the one that we chose here was the weighted geometric mean. We looked at many different metrics, and this one was by far the best one. And I'll highlight some of the features why this was the best one. This is the equations. I'm not going to go through that now, but they're very simple equations that are computed very, very fast. We used the trip data from the city of Comm that has over 700,000 trips, and we processed 175,000 of those. And what we did was we tried to use that similarity weighted geometric mean metric and do the clustering. So this is a visualization of the spectral cluster. On the left-hand side, this is using geometric mean. On the right-hand side, the Euclidean distance. And you can see there's a lot more richness on the geometric mean here. And just to explain what's happening, this is a visualization of the clusters that you get. And the green and the red clusters are those overlapping in space, as you can see, but they're separate in time. And from the other side, you can see these blue and purple clusters that are overlapping in time, but they're separated in space. So the weighted geometric mean was very powerful in terms of identifying very clearly these clusters that can be separate in time and in space and provide better matching. Okay, so we looked at 3 different transportation types. The first is a carpool, where a car goes, picks up the person, and then drops them off and moves on. The second one is a catch a ride, where a person has to go to the ride, maybe using a bicycle, and then they have to go back to their destination, maybe swimming or any other way. The third was car sharing, and in this one we assumed some kind of an autonomous taxi, and they've just been released right now by Waymo in Arizona. Completely driverless taxis, and just drops off people and picks them up and so on. So by analyzing these 3, we got some very interesting results. I'm just going to summarize them here. For carpooling and catch a ride, we were able to achieve 25% and 40% savings in the total traveling distance. For catch a ride, the user may have to walk a little bit. On average, it's about 0.4 miles extra. Not so bad. For the car sharing, we're able to establish chains that can consist up to over 4 pickups. So this basically can reduce the number of cars dramatically that are on the street to actually do the same amount of pickups. And the nice thing here is that we've looked at the polynomial time algorithm using the trick of sequencing and so on to avoid an NP-hard problem of building these chains. So the computation is very, very manageable here. We also did some very nice waypoint matches as well, if you want to also match points along the way. And we did some very good computation here in linear time, whereas all the other competitive algorithms use at least order of n squared. We keep collecting data, and this is about 900 or 870 cams in London. And you get things like the ones on the right here. We're using YOLO, which is you only look once. It's a deep learning algorithm or package to identify objects, and we're using that to automate the car counting and density estimation. But we have some challenges. We had some seagulls photobomb some of the cams that we have, and actually this made the news. So my students were happy that some of the research they're doing was featured in the news, although it was funny. Okay, so I think I'm running out of time. Tamer, do I have time, or should I just wrap up?
I think you need to wrap up because we over time.
So let me skip the applications here. Basically, the application would focus on mobile health, and there is one dimension where you can do some longitudinal analysis and do differential behavioral analysis and try to do early detection of risks for obesity and mobility. The other very interesting thing is identifying these support groups, which we call disease self-management or self-efficacy. And these are for chronic conditions where somebody has to change their lifestyle, like in a diabetes or depression or social isolation. And for that, remember the profile cast and group similarity that we talked about that can potentially be implemented here and so on. So let me skip this. We have a proposal, hopefully for a center that would combine all these different elements together. And lastly, I want to thank my collaborators and students that do the real work. And here are some pointers to you. If you want to follow up on this, you want to use the data, you can also email me. Thanks, and I'm open for questions.
Thanks a lot, Professor Helmy. Just as a round of applause. Thank you. So we are running out of time. So if we have any quick question, we can accommodate one quick question. Professor Helmy, anyone? want to take? I have a question if no one wants to take. Okay, so a quick question, and again, and if it's you think it's if the answer is really too much, or then we can postpone or take it offline. During this whole journey of dealing with the data, how do you see the data evolve over this time? Not, of course, in quantity, I'm talking about the quality. Have you seen like something like, yes, data has really evolved, so I need more interesting tools to handle something like that? Just wanted to
Oh, absolutely. So, all right. So, again, I'm going to try to keep it short. I can give you the longer version later on. So when we started collecting from USC, there was only about 250 access points on campus. And I don't know if you remember those times, you had to go to somewhere like the library and so on to get connectivity. The evolution, of course, happened that now it's ubiquitous. You really don't have to change your behavior a lot to get connectivity. So that actually affected people's behavior on the one hand. On the other hand, there were the device types, going from laptops to cellos, which are the smartphones. And now I think Jörg wanted to introduce guitars, which are, something like tablets or something like that. So definitely the richness of the connectivity and the devices has changed the traces a lot and how we interpret those traces. Another thing that we noticed as well is, again, it became harder and harder to get data because of the privacy issues. But as you saw in the flutes and cellos, we were able to actually, in many years it took us to collect the data, but we were able to integrate mobility and traffic features together. And the inference was very powerful in terms of inferring what the device types are, what people are doing in general, well, not the payload, but their interests and which websites are accessed and so on. So now you can talk about multidimensional spaces that we could not talk about before. So that's from the data perspective. You can talk about predictability, you can talk about correlating traffic to encounters, you can talk about so many different models and services that we could not even fathom before because we were not able to explore that multidimensional space. Add to that the computational power. We have a cluster with GPUs and all of that stuff, and definitely that allows speeds of sometimes times thousand speed ups, and definitely we can explore a lot more dimensions that we did before. I mean, I can keep going on, but I think this would suffice for now. Does that answer your question?
Yep, absolutely.
Okay, right.
Great. Thanks again, Ahmed, for this very interesting talk. And for sake of time, we move forward, and I will hand the chair to Anwar, who will talk about the technical session. Thank you.
Thanks, Tamer. Do you see my screen?
Yes.
Okay, so welcome to the to session 3, aptly named "The Power of Data." My name is Anwar Walid from Nokia Bell Labs, and I am the session moderator chair. So we have 2 presentations. Hopefully we can keep the presentations about like 18 minutes or so that we can have a few questions. So the first presentation or the first paper is invited paper titled Perishable Data in Smart Communities by Dr. Glenn Ricart from US Ignite and University of Utah. Glenn is the founder of the US Ignite nonprofit dedicated to accelerating smart cities. He was previously CEO of National Lambda Rail and CTO of a $2 billion networking company. He's also adjunct professor in the School of Computing at University of Utah. He likes information theory, and his invited talk today on perishable data and smart communities draws on that information theory background. So, Dr. Ricart, you have the floor.
Great, well, thank you very much. I wonder if you could turn on my video.
I think
you cannot start your video because the host has stopped it.
Now you should be able to switch on, right?
Not yet. You cannot start your video. Okay, now I can. All right. Okay. All right. So now you can see me, yes?
Yes, yeah.
Excellent. Thank you very much for the kind introduction. As he said, I'm Glenn Ricart, and the work I'm talking about today was partly sponsored by the National Science Foundation, and it draws on our work in smart communities at US Ignite, and particularly the networking that we need to support the upcoming smart communities applications. And we have a set of tools that will be useful, but they're not complete enough to be able to handle some of the cyber physical system applications we have arising. So I'd like to go and talk about some of these applications. I'll briefly touch on 5 of them, and then talk a little bit about how we can better deal with this information that's perishable. And what do I mean by perishable information? By perishable information, I mean information that, come on, slide, change. There it is. Perishable information is information that decreases in value over time. So information in a smart city that might be actionable right now, for example, actionable for machine language recognition or a part of a cyber physical systems loop, has very high value because it's actionable right now, so it has a high value. However, if there are delays in data delivery, it becomes less useful for that action. It's perishable, its value decreases over time. It might be useful only for machine language training if it's delayed by some number of seconds or minutes. And after a while, it's useful only from an historic point of view that you might want to be able to go back and trace and see exactly what happened. So I'd like to focus on this actionable data that wants to have very short delay in data delivery. And of course, we know something about how to minimize the delay in data delivery. After all, we've figured out to prioritize VoIP traffic over browser traffic. Can't we just prioritize things? And maybe prioritization is one of the actions we can take. But in addition to prioritization, we need to think about the actual information in the packet file, giving them continued priority. I'm going to start by talking about 5 different applications. I'm going to be very brief because I know we're behind time. One is power microgrid coordination. So a microgrid, of course, is a way of having information coordinated between the generation of the power and the demand for that power within a microgrid and between microgrids. And the way that you measure that traffic, I'm sorry, not traffic, it's the amount of power, is using something called phasor management units, PMUs. And those phasor management units are located throughout the power network. And we need to be able to know exactly what was going on in the power network to a time accuracy of 32 microseconds for the PMU standard. And the power grid has to be able to react in less than 10 milliseconds. So you can see from the time the PMU generates its sample, we have to distribute it throughout the data network in less than 10 milliseconds. And if that data does not reach a decision point within 10 milliseconds, we should discard it no matter where it is in the network because it's no longer useful for managing this microgrid coordination. Second one is connected vehicle management. And milliseconds really count. So here you can see a picture of 4 platooning trucks, or yeah, I guess it's trucks. And it's very efficient because they draft one another and they use a lot less fuel. And providing that they are all autonomous trucks, they can follow that closely to each other because they're all connected to each other. In this case, information from the first truck that says, for example, oh, I see something in the road, I need to brake, needs to go to the other 3 trucks so that they brake at almost exactly the same time so they don't run into each other. The time accuracy needed here is a millisecond, and again, the reaction time has to be in less than 10 milliseconds. Another example of connected vehicle management is in intersections. So here's an example that I've taken from some research where you can see that vehicles are no longer stopping in general. Sometimes they do in order to avoid collisions, but there is much better use of the intersection, and we're not having situations where the vehicles are always stopping and restarting, which uses a lot of fuel and adds to trip times. So intersection sharing is clearly an application of the smart city future, in which it's very important to be able to have very strict time accuracy to about 1 millisecond, and again, react in less than 10 milliseconds to be able to avoid collisions in the intersection. Another application is managing ischemic stroke. This is a medical application. You can see at the top right here a mobile stroke unit. It's like an ambulance, but in that ambulance, you can see in the bottom is a portable CT scanner. And that's because if somebody suffers a stroke, which is a blockage in the arteries, every second the patient loses 32,000 neurons, about 230 meters of synapses, and I'm sorry, 230 million synapses and 200 meters of axonal fibers. Now there's two treatments depending on where the clot is located. So administering transmembrane plasma, I can't pronounce it, TPA is what everyone calls it, can either cure or kill the patient. And it depends on where that blockage is, and it depends on the CT scan saying where that is located. The image is about 100 megabytes, and the brain continues deteriorating while this information is sent to a very skilled physician who has to look at the CT scan and decide whether TPA is appropriate or whether they need to be rushed for surgery. Time accuracy of a second, and the reaction, of course, is in as few seconds as possible. Earthquake prediction and notification. We've discovered that in earthquakes, there's something called the compression wave, the P wave, which arrives, in this case, about 7 seconds before the damaging shear wave, or S wave, that actually does most of the damage. In that about 7 seconds, and it, of course, depends on how far away the center of the earthquake is, it could be 1 second, it could be 15 seconds. It's very possible in many cases to stop equipment, bring traffic to a halt, stop an elevator at the next floor, so that the damage from the earthquake can be minimized. Again, very critical information. We need time accuracy to about half a second and react in half a second before the damage in order to be able to deal with that smart city application. And in that about having to do with flutes and cellos and bassoons. I played a bassoon, Ahmed, so I'd like you to figure out how it's very possible in many cases to stop equipment, this music performance in a COVID-19, so that the damage from the earthquake can be increases, but they would like to be able to sing as an ensemble together. And that can be done, but we need very short packets and very frequently, and bassoons. I played, so I'd like you to figure out how marching bassoon did it. Simultaneous music 19 era. All these people are in separate, they would like to be able to sing as a that can be done, but we need very hardwired networks because come in the past month or so to be very popular called Jack Trip, where these tens of milliseconds really count in simultaneous music performance. So another smart city application. So in all of these applications, we have some known approaches for handling it. All buffering is harmful. You never want to buffer. You want to sample just before you send the data. You want to pre-allocate time slots, as is done in 4G and 5G, resource reservations. These are all techniques that we know how to do. In the interest of time, I'm going to skip the rest of this slide because many people know these particular techniques, so I just wanted to point out that they are applicable. However, and there are standards for doing that, and this is all in the paper, so you can go and read about those standards for deterministic networking and for time-sensitive networking. But because it's perishable, the information, we ought to look at some cross-layer things that we can do. Do all messages have the same information value? And the answer, of course, is no. Let's take that very first one, the microgrid. If the microgrid demand is steady, then that information is of much less value than the message that the microgrid demand has dropped 50%. 50%, we need to do drastic things to coordinate the microgrid. So messages have different value depending on how expected they are in these smart city applications. And that suggests looking at the information content, which is the amount of surprise, or sometimes called surprisal, or S, of receiving this perishable information message about an event E. It's a function that decreases as the probability of an event E increases. And you can see there the formula at the bottom. This is known part of information theory. The value of the information depends on how much it surprises the receiver. Now, if you look at that formula, you may remember that that's very similar to Shannon entropy, eta of an information source, where eta is equal again to a negative probability of an event. So knowing this, we ought to be thinking about how to send that information. And the information depends on the previous information of what you previously knew. So on this slide, and you can read in the paper, you can use a random variable to represent the current state, another random variable representing the state that's known to the other side, the state reported some time ago. So the shared information state versus the new information that you have. And information theory shows us that the eta is a conditional eta in that case, a conditional probability, which I won't do the math for because we're running out of time. So here's the payoff slide. This is the new approaches for handling perishable data. Well, one is we want to keep packets short so that we minimize serialization time, deserialization time. We want to send differential information from the last, you might call it the key frame, or the last time that we had established that we knew exactly what was going on. We can use a bad news travels fast approach that prioritizes based on the surprisal and the application criticality. There's lots of techniques that we might employ here to ensure delivery. For example, replicating frames, using forward error correction for these smart city applications, deciding when to send keyframes, sending over multiple paths simultaneously. If we have backup paths, because we've got the ability to fail over for these critical applications, it may be much useful to be able to use those multiple paths simultaneously, even when they're both working, because one path might be somewhat faster than the other, or less restricted, or less loaded, less buffering. Include predictive information if it's available, request acknowledgement, and keep sending critical information to make sure that since we're not doing acknowledgements in TCP, that we get the information through. Adjust the sampling interval if the situation warrants that. Less critical information can do less frequent sampling. Always send the most recent data. Let the older messages be overtaken with any newer ones containing differential information. And the checklist of tools is at the end of the paper. And with that, I'll just note that we've got a conference coming up at US Ignite on smart cities. It's October 27 to 29, and if you would like an admission to that, that's free, let me know. I can take care of that. So that was the very quick version. Do I have a quick question, perhaps?
Hi, yeah, if you have any questions, please go ahead.
I probably went through it too quickly for some people to grasp.
I have one question while maybe others are preparing. How about the role of prediction in this setup, statistical prediction or machine learning to predict the next very event?
Very excellent question. So it turns out that the prediction affects the conditional probability, because the way I stated it, it's the shared information versus the new information. But if you have the ability to predict, if we can go and take a look at, for example, some of Ahmed's predictions of what the traffic is going to be, then you can do a conditional probability against that prediction. And to the extent that the prediction is more accurate than the current state, then that alters that conditional probability and reprioritizes the traffic. So excellent question. Good job there.
Yeah, that's good. I see Zhi-Li Zhang has a question.
Right. So Glenn, really great talk. So I have a question. Since US Ignite has been involved in a lot of smart city type of application, is there any effort actually going on trying to collect a lot of data? Because we know that data is actually really important for a lot of the application, for example, you talk about. Are there kind of concerted effort from the cities and other places trying to collect some of the public data?
Absolutely. The US Ignite has released a smart city data structure, a way of formatting the data about smart cities. That was just about a month ago. It's on our website. We're working to get adoption of that by both the companies. It was a combination of 12 of our communities working with about 12 companies operate in this space, because we wanted to make sure that both the commercial and the research data would be the same. And we are working with a couple of our communities. Las Vegas is one right now that is beginning to provide their transportation information, and they're going to share it within Southern Nevada among the various municipalities there using that. So I recommend going to our website and taking a look at that. And otherwise, send me an email message. My email is glenn.reichert, glenn.reichert@usignite.org. And I would be glad to go and send you a link to that.
Great. Thank you very much.
You bet.
Any other questions?
Yes, I have a quick question.
Sure.
So how is this perishable data is different from the information of age that is being discussed in the networking community these days?
Right. So age data is certainly related. This takes a bit more of an information theory approach than the aging has in the papers I've read.
Any other questions? So Glenn, now I also heard about in Salt Lake City, there is with 5G, there is big efforts there.
Right. There's a powder project on the power, and that's the power.
Right, the power project. So I think are there planned activities there with the 5G coming up?
So as Tamir was saying, there is also work at US Ignite in advanced wireless research. And of course, latency in advanced wireless research ties right into the work I've just been reporting on. There is 4 test beds. One test bed is in Salt Lake City at the University of Utah called Powder. It's part of the Power set. Powder focuses on massive MIMO, which allows for more data to be sent over a wireless link, beamforming using massive MIMO, and the ability to have very software-defined stacks involved. So, for example, US Ignite is a member of the Open RAN Alliance, where people taking a look at that. And so, yes, it's a test bed that includes downtown Salt Lake City. And we are looking at combining the standard data formats and sending together with critical CPS data for applications using wireless, using the Powder test bed.
Okay, great. Well, thanks, Glenn.
You bet.
We appreciate it. Let's.
I have a quick question.
Oh, yeah, go ahead.
So thanks, Glenn, so much for this talk. It's very interesting. I just wanted to touch upon the monotonic decrease in the value of the perishable data. And I wonder if it's really monotonically decreasing, so the more recent data carries more weight and importance than the ones far away, or something may have happened a week ago, maybe more important in predicting the future than something that happened maybe a few minutes ago.
Yes, but the thing that happened a long time ago is already known. So it's really, the reason it's continuously decreasing really has to do with the relationship with entropy. And if you know that something happened a week ago and you build that in, then that's not new information. So again, the conditional entropy is really the one that counts, and that depends on what you already know and or predict based on what you already know.
Right, that makes sense. But I mean, the importance or the weight of that information for the prediction, that's what I mean, yes, you know that it happened a week ago, but how important it is to predict the next step.
So the prediction of the next step depends on the information that you have, the information you've just received, and how you want to factor that in. So the work that I've presented doesn't say how you weight that in any way. It may be that there are processes where the recent reading doesn't really apply very much, but the 5 applications I showed you are all ones that do. So I will try to think of some applications. It's certainly theoretically possible that there are some that the most recent sample doesn't make much difference, but I'll think about that.
All right, thank you very much, Glenn.
Thank you.
Thanks. Any more questions? Okay, then thanks, Glenn. We'll move to the next presentation. Sure. Okay, so now we move to the second presentation titled Anomalous Model-Driven-Telemetry Network Stream BGP Detection by Rostand, Fezeu, and Zhi-Li, Zhang. Rostand is a third-year PhD student working with the networking lab at the University of Minnesota under Professor Zhi-Li Zhang. His research interests span bridging the gap between network experts and machine learning experts. He works on problems related to network automation, self-driving networks, and network control and management. He's also interested in problems related to the 5G network core and also attack problems related to IoT networks. So Rostand, please go ahead. I'm gonna stop sharing.
Okay, can you guys hear me?
Yes, we can.
And can you guys see me?
And see you too.
Okay, thank you. With that, let me see if I can share my screen here. Wait, can you guys see my screen?
Yes.
Okay, I'm not sure how to get rid of the subtitles here. It's my PowerPoint, so I'm just gonna go through the presentation right now. So, hello everyone. Again, this is Rostand, and today I am going to present our recent study, Anomalous Model-Driven-Telemetry Network Stream BGP Detection. This is joint work with Professor Zhi-Li Zhang from the University of Minnesota. Traditionally, network operation and management tasks rely on mechanisms and tools such as a simple network management protocol, SNMP, syslogs, and CLI commands. These protocols provide only slow, that is every 5 minutes, coarse-grained, incomplete, and often specific information that is hard to operationalize. Recently, model-driven telemetry has been developed and is widely adopted by several vendors. MDT leverages the power of models to implement high frequency in the order of seconds, push-based approach. MDT data is granular and provides fine-grained visibility of network devices, enabling data processing in near real time. As a result, it is possible to achieve network automation at scale. However, processing these huge amounts of network device level data streams to obtain network visibility and deduce network conditions for operation and management decision-making, like anomaly detection, is still very challenging. Take commercial enterprise data centers as an example. Many vendors like Facebook, Google, Amazon use BGP as the only intra-routing protocol instead of conventional OFPS, IS to take advantage of rich path diversity in data center topologies. Several vendors like Cisco, Juniper Networks, Arista, and Huawei have developed BGP MDT data models using the Yang models over NetConf, ResConf, or Google gRPC protocols. The Yang data model is data structure that defines hierarchical data, where each node on the network have several sensor groups assigned to it. For example, the Cisco IOS XR 6.2.2 Yang hierarchy comprises roughly 378,000 lines of code with over 45,000 sensor groups described. Approximately 6,000 of these sensor groups are related to BGP protocols alone. Yang data model is also standardized across different vendors. Thus, this rich high-frequency, push-based MDT data calls for rethinking operational management tasks, especially anomalous detection, which is the focus of this presentation today. This slide highlights our major contribution in the paper. In this paper, we study anomaly detection using BGP MDT from a large data center network as a case study. Our work improves upon outlier density proposed in SICM 2018. Outlier density leverages density, an unsupervised clustering technique for real-time detection of anomalous MDT data. We start by engineering a systematic MDT data processing and feature selection framework that we call Bravo. Bravo is specifically designed for network MDT data via the Yang model. Next, we formulate two unsupervised learning mechanisms. The first, time proximity netcode downstream, achieves a 59% reduction in the number of alarms raised on the data center network compared with outlier downstream, therefore increasing precision at the expense of a slight delay. The second, signature proximity netcode downstream, helps network operators in troubleshooting alarms. Signature proximity netcode downstream presents operators with features affected in an alarm raise. And lastly, we make freely available all the datasets, scripts, and code used in this study on GitHub. In this slide, I present Bravo. Again, for the sake of time, I would not go into the details of Bravo in this presentation. However, I would like to highlight that Bravo, while designed using Cisco Yang data models, is portable to other MDT vendor workflows. Bravo processing pipeline is modularized, and each module contains a readily available toolbox with a variety of techniques suitable for MDT ML tasks. We validate Bravo by performing a domain expert control and data plane feature selection approach. Now, let me introduce some brief details about our MDT datasets used and the annotated ground truth labels. The first dataset used in this study is the MDT dataset open sourced by the contributors of Outlier Density. This dataset was collected on the physical network with 12 Cisco XR Release 6.2.2 routers. The BGP protocol is the only routing protocol configured on the network. We engineered the second data used in this study. This data was collected on the virtual lab with 6 Cisco XR Release 6.2.1. On this virtual network, other sensor groups besides BGP-related sensor groups are configured on the network, significantly increasing the length of stream. Every 5 seconds, the routers push pre-configured telemetry features to a centralized data collector. After a normal period lasting about 240 seconds between experiments, controlled anomalies are injected on the network and the annotated ground truth labels are recorded. To validate the ground truth labels, this figure shows the pad count for a VRF feature for a BGP clear experiment. The line band indicates the ground truth start and end times. The BGP clear command triggers a pad count reconfiguration on the routers as shown. Since the pad count reconfiguration happens when the BGP clear command anomaly was injected on the network, the correctness of the ground truth labels are validated. It is important to mention that we will use these labels only to assess the performance of our models. Next, let me introduce dense-stream and outlier dense-stream. Dense-stream is a streaming clustering algorithm. It uses a damp window model. Dense-stream assigns weights to each data point, and this weight decreases exponentially with time via a fading function, highlighted here, where lambda greater than 0 is the decay factor, and t is the time at which the data point arrives. The algorithm also uses the concept of outlier microcluster and potential microcluster to distinguish between normal and anomalous data. In 2018, outlier dense-stream was introduced by Rosie and al. In their paper. Outlier dense-stream is an anomaly detection engine based on dense-stream for real-time detection of streamed anomalous MDT data. It is governed by 2 criteria: temporal order, KT, in which each node on the network operates individually, and an alarm is raised upon reception of k consecutive outlier samples at a node, and spatial order ks for multiple nodes during the same time slot. However, major drawbacks of outlier dense streams still exist. The first drawback is that the total number of alarms raised is still very high, which may overwhelm data center network operators. And secondly, the number of false alarms is also high, resulting in a waste of resources. Thus, in this work, we take a swing at addressing these drawbacks and advance netcode density. To reduce the total number of alarms raised, we intelligently correlate different alarms raised by different nodes on the network and introduce the concept of time proximity netcode density, TPK delta. A time proximity alarm is raised only if node Ni detects an anomaly at time t, and at least k neighbors of node Ni flags a sample as anomalous at time t plus delta. Particularly, if the ground truth labels the system to be in normal state, and node I and at least k neighbors of node I flags a sample as anomalous, we observe a false alarm. Next, to bring forth anomaly heuristics that aid during early troubleshooting steps, we introduce signature proximity netcode density, SPK delta. SPK delta presents counter values beyond one standard deviation from the mean of historic data involved in TPK delta alarms at time t plus delta. That is, SPK delta goes beyond TPK delta alarms to help network operators during their troubleshooting steps. So before we start showing the evaluation results, here we present the evaluation setup. We use an Intel Core i5 MacBook Pro with 16 gigabytes of memory, and we also implemented outlier density, the comparative method, and our benchmark netcode density. We use both the open source and the virtual lab MDT dataset for all of our experiments. We start by evaluating Bravo. The dataset obtained after Bravo processing has at least 60% feature overlap compared with the domain expert control and data plane feature selection approach. Moreover, we evaluate the efficiency of Bravo. As shown in this figure, Bravo takes less than 3 seconds to process 100,000 data points and about 33 seconds to process 1.5 million data points. Therefore, Bravo can comfortably handle high-speed data streams. We further demonstrate the benefit of Bravo while showing that it achieves better precision compared with the domain expert selection approach. Next, we evaluate time proximity netcode density, TPK delta. We start by comparing the number of alarms raised by outlier density and netcode density. This figure shows that netcode density with delta equals to 5 can intelligently correlate different alarms raised across several neighbor nodes, thus achieving a 59% reduction in alarms raised when compared with outlier density. Here, we want to show how varying k and delta significantly affects the number of alarms raised by TPK delta. Observe that when delta increases from 5 seconds to 60 seconds, TPK delta alarms generally decreases. This is because TPK delta alarms less than delta go unnoticed. Additionally, increasing k from 1 neighbor to 5 neighbors decreases TPK delta alarms. Again, this is because monitoring more neighbor nodes reduces the likelihood for TPK delta alarms, especially if the underlying traffic is not routed via all k nodes. And lastly, to evaluate TPK delta, we contrast the precision, false alarms, and delay obtained for alarms raised with Bravo and the domain expert control and data plane feature selection approach. Note that while it is possible for single node alarms to go unflagged, we assume 0 false negative. First, we keep k fixed and vary delta. Notice that all performance metrics exhibit the same behavior per dataset regardless of the feature selection approach. However, especially observe that using Bravo yields a higher precision, reducing the number of false alarms at the expense of a slightly delay. In the second experiment, we kept delta fixed and varied k. Similar observations are made. For the sake of time, the table for this experiment can be found in the paper for interested audiences. Lastly, we evaluate SPK delta. In this figure, we show the system state at time t plus delta for two neighbor nodes. The line band shows one standard deviation from the mean, and the blue band represents MDT data stream at time t plus delta, and the blue line, represents MDT data stream at time t plus delta. Notice that SPK delta is able to deduce that similar features are involved in anomaly for both nodes. These features as shown here are 4, 5, 7, and 11. By identifying these features early on after the alarm is raised can provide network operators with the first insight into what might have caused the alarm and further use domain knowledge to quickly troubleshoot the alarm. Now, to wrap up, in conclusion, several takeaways can be highlighted from this study. K and delta are tunable parameters set by network operators. On one hand, operators who care more about precision at the expense of delay can set a higher K and a small delta. On the other hand, operators can set K small and delta high to reduce the number of false alarms. And finally, SPK delta allows network operators to quickly troubleshoot alarms. So to wrap up here, this work introduces Bravo, a systematic data pre-processing framework geared towards the Yang data models. We also advanced netcode dense-stream, in which TPK delta outperforms outlier dense-stream by achieving a 59% reduction in alarms raised at the expense of a slight delay. SPK delta presents network operators with MDT data features involving alarms. And finally, we open source all our data, all the data set and code used in this study. These results open up for further work in the following directions. Given the low complexity, the low computational complexity of dense-stream and performance, it possibly might be a good idea to run different models in parallel and each detecting a specific anomaly type. And then these models can further be complemented with a micro model that would make the final decision about whether raising an alarm or not. Also, experimental study of the maximum number of features that should be exported given a specific network task is necessary because the Yang data models are, the features are exorbitant. And with that, this will be all for this talk. Thanks for listening. I hope I did well in time here. So, and then I'll take any questions if there are any. Thank you.
Yeah, great. Thank you, Rostand.
Yeah.
Let me open it now for questions. If you have a question, please go ahead.
This is Glenn Ricart. Could you comment on the application areas that you think will be, that this approach will be most useful for, especially if you have one in smart cities? I'm always looking for a smart city processor.
Right. The application area that I mentioned at the beginning of this presentation is mainly data center networks that have this Cisco or have these routers that run the Yang model. However, in the smart city, I know that some like in the backbone, sometimes you might have these routers that are maybe off the shelf from Cisco that is help in routing this data. And if this router support the Yang data model, then this can be even applied to a smart city framework. I don't know if that answers your question.
It does, and in a number of cities, there's multiple networks because there's commercial networks and municipal networks all working together. And
right.
The ability to go and combine them intelligently at what we tend to call a digital town square might be able to use this work. So thanks very much for it.
Thank you.
Okay. Any more questions? Rostand, I heard you talked about injecting faults. Is that?
Yes.
Can you elaborate on that?
Yeah. So what we did is that to trigger the anomalies, we manually injected anomalies on the network because again, we did just a proof of concept work. about the idea. So what we do is that we have the network, and then we give a time lapse of about 5 minutes, which is about 240 seconds, and we consider that as normal, in which there's no traffic on the network and nothing is going on. So the data that is collected during the period we use that data as our normal traffic, and then now we send traffic through the network, and then we manually inject anomalies. For example, BGP clear. We issue a BGP clear command at the Cisco router or the router, and then in the background collect the data. Also, we log the start and end times, and then we also have we also trigger anomalies like port flapping, where we manually simulate via a script, a port flapping, and then we collect the data. So those are the type of anomalies that we triggered in the network. I don't know if that answers your question.
Yeah, no, that's good. Yeah, and it just reminded me of what Netflix does in Chaos Monkey, injecting, but they're injecting it on operating network, and they do have replicas and so to recover. But
Right. But yeah, all of this is simulated. So even the physical network was an isolated network. Even the virtual network was an isolated network. So all of this is simulated. So
yeah. Okay, good. Okay, any more questions? Okay, well, thank you, Rostand.
Yep,
and
thank you.
And thank you, Glenn, for your presentation. So this concludes this workshop. Thank you all.
This
So thank you.
this is session, concluding the session. So we will resume again in less than 20 minutes, 18 minutes for the panel discussion, which I have interesting 4 panelists with our 2 honorable moderators.